Howdy. We're Senior Design Team 13 from the Biomedical Engineering Department, and we've been working on a project sponsored by UT Southwestern Medical Center that we've called LC Vision. Initially, the need for our project came about as the demand for remote medicine increased, as it has been steadily in recent years. Patients that live in remote or underserved areas have difficulty obtaining the treatment, basic or specialized, that they need without long, and with some conditions, dangerous commutes. For these populations, platforms to perform clinical assessment and obtain physiological data remotely would be of high utility for the safety of the patient, for the expediency and ease of use for the quality Medicare, and for long-term condition monitoring. In a field that is becoming increasingly personalized in its approach to medical care on a patient-by-patient basis, cheap, easy, quick, and accessible testing is demanded. However, as the world changed over the course of the past semester, so did our need statement. The COVID-19 outbreak transformed the way non-emergent medicine is performed in the present day, and what was to become the future with telemedicine became the present. There is now more of a need than ever for ways to evaluate patients while maintaining the present shelter-in-place orders and social distancing. Our team wished to meet this boldly with engineering.
Since our sponsors from Southwestern deal in the field of neurology, we were tasked with addressing telemedical evaluation of low-contrast visual acuity. Simply put, this is a patient's ability to distinguish a grayscale character from a white background. This ability decreases in the presence of different neurological disorders or conditions like multiple sclerosis, which is estimated to affect over 1 million people in the US, and optic neuritis flares, where the optic nerve becomes inflamed from infection or disease. Low-contrast visual acuity testing quantifies the extent of this ability and provides a useful metric in the clinical evaluation of these patients. Given the clinical need for a way of assessing low-contrast visual acuity remotely, we could then identify our problem statement to be create a platform for remotely administering a low-contrast visual acuity test that is easily deployable and easy to use. With this in mind, we set out to understand our task, the requirements of our stakeholders, and the current market for solutions addressing it.
Discussion and reading up revealed that a low-contrast visual acuity test in the clinic is performed like a regular vision test, in a dark room, lights off, with a well-lit panel displaying a set of 60 uppercase letters at a grayscale contrast level of 2.5% in rows of 5, decreasing in size logarithmically every row. A clinical administrator prompts the patient to read the letters from a set distance of 2 meters, and the patient's accuracy is recorded as their score out of 60. Should the letters become too small or too difficult to see, the test administrator is allowed to encourage the patient to continue up to 3 times according to standard LCVA protocol. After 3, the test is terminated and the score is reported as the number of characters correctly identified out of 60. From interviews with our sponsors, the project user requirements were identified as shown here. The application, first and foremost, needs to work. It needed to present an accurate reconstruction of the low-contrast visual acuity test with methods based empirically in the protocol. In order for a patient to use it without a test administrator in the clinic, it also needed to be able to configure its own environment. That is, to react to different ambient lighting, the device's stability, and the patient's proximity to the screen. Beyond that, it needed to be user-friendly. The patient needed to be able to intuit their way at least to the tutorial screen and to progress steadily through the test on the first try. Other necessary characteristics describe the application's functionality in interaction with simplicity, brevity, and fast score reporting. One layer beyond the application itself, a means of controlling it and reading scores was desired.
Literature review of current solutions reveal that there are no mobile applications used to administer low-contrast visual acuity tests outside of the clinic. The nearest competitor was Clinic CSF, an Apple-based software that measures contrast sensitivity function with Apple devices in the clinic. Contrast sensitivity function, as opposed to our identified metric being low-contrast visual acuity, measures visual acuity over a range of contrasts instead of specifically a single low contrast. Clinical CSF was also constrained to in-clinic deployment.
After further research, we have concluded that a mobile application that a patient can use to self-administer at the prescription of a physician a low-contrast visual acuity test would be novel and address our problem statement directly. Developing in Android Studio and Firebase, we resolved to produce the following prototype application: a downloadable Android-only software that administers a low-contrast visual acuity test letter by letter, reporting scores to a test project in Firebase as per the standard LCVA protocol. The letters are displayed at a 2.5% contrast and scaled logarithmically for the distance the patient sits from the phone. Configuring at just past arm's length, 1 meter, it employs the light sensor of the host phone to monitoring ambient light, the gyroscope for stability, and the camera for patient proximity. Should valid ambient parameters to disturb the light raising above 2000 lumen, the phone moving around and being unstable, or the patient goes too close to the screen, the test is paused until conditions are met so as to not invalidate the results of the LCVA score. With the standard keyboard for patient observation of letters displayed, there is also an I don't know button substituting for test administrating coaxing in a clinical text protocol. When the I don't know button has been pressed 3 times, the test terminates early and the score is reported at the number of correctly identified letters to Firebase.
Okay, so just a quick demo of our application here. We dismiss our IP agreement at the front end, and then here's where we input our patient ID. This will be something provided by the doctors prescribing this test to patients, and here we're simulating with 111-111. And so we start the test, and the first step that we do is calibration with the camera. And so what you're going to do is place your face at about 35 centimeters. And just a quick note about how the phone's working. It's broadcasting to Zoom right now, and it's also on low battery mode, so it's running a little slow. But we'll see that he calibrates successfully and then moves back to a distance of about 1 meter. And the test is configured so that beyond 85 centimeters, the test will actually start, assuming all environmental conditions are approved. And so this letter is going to display for 5 seconds. And then we see that Joseph's going to lean forward and input the letter that he just saw. In this case, it was an R, so we have the correct response for the first letter. And then moving back again, we see beyond 85 centimeters, it displays the next letter, which here is an I. So we see it display for 5 seconds. And we see him lean forward and input an I. And so after this letter, he's gonna show us the light sensor functionality. And so we'll see him pull out his phone light and shine it at the camera. And so once this environmental condition is violated, we'll see a little pop-up here. Device is receiving too much light. Please move to a dimly lit area. And here's where a little bit of the computer slowdown kicks in. But once these notifications clear and he moves back past 85 centimeters again, we will see the next letter pop up. And here it's a T. Displays for 5 seconds. Then he leans forward and inputs a T. After this, he's going to show us the functionality of the I don't know button, which simulates the encouragement that you receive from the clinical administrator, if you're the patient, in the in-clinic setting during the actual protocol. And so once he presses this I don't know button 3 times, the test will terminate and the score will be reported to the Firebase. And so after a third I don't know here, we'll see a notification that says note saved. And that would be the score getting transmitted to the Firebase. So flipping over to our PC view and logging into our Team Firebase account, we get to the Firebase dashboard and our project LC Vision, pulling up Cloud Firestore, and then we see each of the documents that have been generated because of patient scores being sent to it. And so we have a few here, a number of test subjects, and then we're looking for patient ID 111111, and we see our correctness score of 4 out of 60. Given the present need for means of remote clinical evaluation, we believe that many projects like LC Vision will arise in the coming months of biomedical engineering. Research and design for our team has proven a great learning experience in practical engineering and tangible design solutions to real-world problems, and we hope that our mobile application can be a good starting point for more development, something that helps patients get the treatment they need. From the LC Vision team, thank you so much for listening. We hope you enjoyed. Thanks again, and gig 'em.